First day at school here, Camp.
I don't know exactly how. When your bikes kick off.
School. Where's that? Do you get any handouts?
There are some handouts.
Oh, excellent.
I took what they critiqued on your one. Right, okay, so welcome everyone to the introduction to chemistry. My name is Pelham Gayts. I have a background in natural sciences, specialising in physics with a strong background in chemistry. None of you have met each other before, so I thought it might be good if we just go around the room introducing yourself and any sort of previous learning that you've had in this subject.
My name's Tony Gates. I got a GCSE grade 1 in chemistry, but I did fail my chemistry O-level.
My name's Paige and I've got GCSE level of chemistry.
My name's Tracy Gates. I'm a mum and I have to care for my father, and I have done a baby first aid course before.
Okay. So from the initial interviews I had with all of you, I've noticed there's a good spectrum here from everyone who's educated to a level 3 grade, so that you're either coming from an MVQ in practical skills all the way up to an HND in engineering. So there may be a bit of a sort of spread in the class, so if anyone's got any questions, don't be afraid to ask them. And I may even get a call on some of you that do know this particular one to answer it for the others. Okay? So, there's a couple of learning objectives we'll have from this session. So the first one is to introduce each other and myself, which I think we've all done. The second one is going over the ground rules and the venue rules for this first session we've had here. So I'm just going to hand this out for you. It's just the ground rules and venue rules here. So they're quite basic, although that they're the overall rule with things. So the first one there: respect each other, don't talk over each other, don't sort of think negative, don't sort of make fun of those around you. I've seen that one of you has already seen the no mobile phones, so keep them on a silent mode or a mode that won't distract others, although if there is ever a pressing emergency, well then I'm sure we can find some kind of compromise. Okay, and the rest of the rules there you can read over in your own time just to save time. There's also a few venue rules that are put in place by the building owner. Don't plug any phone chargers in the wall unless they've been pat tested. If you're not sure what that is, then they probably haven't. Just make sure that any exits are clear, don't put bags or coats or anything in. And just as a reference, the nearest fire exit is out of this room to the right and the door at the end of the hallway. Okay, so, and what I'll have you do is at the end of the session I'll just have you sign these and hand these back in. And do feel free, if ever there's anything you'd like to change about them or something you think it would be better if we changed, feel free to talk to me about them. Okay, so now going into the actual work. So in this session we'll be learning the definitions of an atom, an element, compound and a molecule. And also we'll start on the basics of reading and understanding basic chemical formulas. So we'll understand what they're talking about. Okay, so moving on to the work. So chemists like to view the world as a sum of their parts. Many sort of things we see in our day-to-day lives, say a car, or a house, or a town, or a country, we view these as a single object. And yet actually what we should do is view them as a collection of many thousands of parts that go into them. So you see here all the parts that go into making what we previously viewed as just being a single object. Now the important part to take from this is that when we put all these pieces together, we don't lose the original piece, making a car. When you put these tyres into the car, we don't lose them, we still have them. A steering wheel is a steering wheel, whether it's inside a car or outside of a car. Now just as a mechanic, views these things as a sum of its parts, chemists have attempted to do the same by cataloguing everything in the world as a basic set of elements. So who knows what this is? Page?
Periodic table.
Yeah, the periodic table. Even those that aren't very well acquainted with science will know that's what this is, or at the very least has seen it, maybe in pop culture or sort of another subject at school. Now what the periodic table attempts to do is it attempts to break everything down in the world that we see into this collection of elements. Now there's a couple of definitions we'll need to learn for this, because although this originally started out as an exercise to simplify the world, as you can see actually it's quickly got out of hand. There's now over 121 elements known and isolated. This is an old one, it only goes up to 118. So there's a few definitions we'll need to learn before we can get comfortable with viewing chemical formulae. So, does anyone know the definition of an atom? Or how would you describe an atom? Anthony?
It's what bombs are made of.
It is. It is what bombs are made of. Okay, so an atom is, although I said that elements were the fundamental building blocks of everything, an atom, just to explain, is the basic building block of everything. Elements are made up of atoms, but because there's not much diversity in these atoms, we can kind of just write them off for the time being. This won't be the focus of it. It's just important you recognise them, because that'll be what the demonstrations and any images we use will be represented by. So what about an element? When does an atom become an element? Or stop becoming an element? Tracy?
Is it when it's broken down?
Well, an element can be broken down into atoms. And in fact, an element is any single type of atom. So one atom of a particular element on its own is still an element. Two atoms of the same type are still an element. But we'll see what happens when we start mixing these up with compounds. So as a general use word, what would you describe compounds as? Don't worry about the technical definition for this, but what would you use it for in everyday speech? Paige?
More than one thing put together.
Yeah, more than one thing put together. In this case, a compound is when there are atoms of different elements. So we've got more than one element mixed into that. And then we have molecules, something that everyone's heard of, but may not know the exact definition of what a molecule is. Does anyone want to take a guess at that? Anthony?
Seem to remember it comes from something like moles, which is a predefined collection of elements that come together to make the smallest unit or something of a particular compound.
It's funny you say that, as the smallest unit. That's all a molecule is. It's a single unit of either an element or a compound. It can even be a single atom on its own, if that's all there is collected together. So we'll have a quick exercise on that then. So with the first picture here, what is in that box there? Is it an element or is it a compound? Oh, and just so you know, you see there are different colours. There's nothing specific about them, it's just they use colours as a way to differentiate different elements. There are some people go back to the same colours, but they're not agreed upon. So although some people say yellow is for sulphur and black is for carbon, not everyone agrees with that. So if you do use colours, usually they'll be, if it's important, they'll be labelled or there'll be a legend for it. But in this case it doesn't matter, these could be absolutely any elements. So what is going on in the first box? Is this an element or is this a compound? Tracy?
Element?
Yeah. What made you say it was an element?
Because it was singular.
Yeah. So each of these balls in each of these pictures, they represent single atoms. But as you rightly said, there is just one type of atom in there, so that's an element. Now what about the second image? Is that an element or is that a compound? Anthony?
I'd say that's an element because you said earlier that an element can be made up of more than one atom, providing it's the same type of atom and they're both blue. So.
Yeah, exactly. So because there's one colour inside this box, it indicates there's only one element in it. And so although it may look slightly more complicated than the first one, they are both still elements. There's only one type of atom is together. It just so happens that these are bonded together and these aren't, which can happen depending on where on the periodic table the element is. But we won't go into that this session. Anthony?
So the first one could be atoms or element.
Yes.
Right, okay.
For this level though, because we're viewing everything as elements or compounds, you're right, it could also just be called atoms on its own. But just to make it flow between the topics, we'll refer to it as still an element. What about this third picture here then? Is this an element or is this a compound? Penny?
Compound.
Compound, yes. What made you say that?
Because there's two colours stuck together.
Yes. So as you can see on the outside we've got three yellow balls and in the middle we've got one blue one. And so that's a compound because we've got two different types of elements, two different types of atoms are joined together on that. And what about this one here then? Is that an element or is that a compound? Anthony?
Well, I would have said it's probably a compound because it is made up of lots of different elements. But it's a compound that's also made up of elements and other compounds. So it could be like cake, like lots of different ingredients come together to make a solid mass of material.
Yeah. It is a bit of a trick question. It is just a mixture of things. So we can actually have a mixture of elements in which the individual pieces are still called elements. Because say for example we didn't have these yellow and blue ones, we would have a mixture of these single atoms as an element and these double ones as molecules of elements. Now just because they're mixed together doesn't make that any less of an element. So here you see they're bonded together, so they're actually stuck together. No matter what you do, they're going to remain together. But with this, we could quite easily split them apart because they're not actually connected to each other. So we wouldn't refer to everything in this as a compound just because there's a mixture of things in here. It is just a mixture of different types. So it happens to be a mixture of the first three. Okay, so we'll have a look then at chemical formula. So going back to the periodic table, you'll notice here that there is a symbol above for these different elements. So no one ever refers to, say, carbon as just C in normal conversation. But you see a lot of them do match up to their names. B for boron, C for carbon, N for nitrogen. Where it becomes a bit different is you see over here we have Na for sodium. Now you'll notice in sodium there is neither an N or an A. But what this demonstrates is just the international community in science. So sodium was originally discovered and isolated by a German scientist and he called it natrium. So if you're in Germany and you are talking about sodium, they will call it natrium. But to prevent these language errors coming up worldwide, because you think if you wanted to practice chemistry in Germany or Spain or Italy, popular places for research, you'd have to relearn everything on this table in the local language. So to help make sure that there's no errors made by that in the working, everyone has agreed upon symbols, letters for each element. So we use these letters more than we use these words, because when you write this, it's much like mathematics. When it's written on the page, no two people can argue about the meaning written on it. They understand what is being spoken about. Instead of if we put sodium and we wrote SO as a shortening of sodium, well then that would confuse someone else because they've never seen it before. So quite commonly when we see chemical formulae, we won't see them written out with their English names. They'll be written using all of these like shortenings for them. And sometimes they don't make sense, so it becomes a bit of an exercise in memory for them. But memorising them right now isn't so important. So here's an example then of a chemical formula. So here you see we've got a number of different elements together. So a number of them together would be called a what? Bearing in mind that they're bonded together. Tracy?
An atom.
It is made up of individual atoms. Anthony?
It's a compound.
It's a compound. As Paige said earlier, you would use compound usually refers to more than one. And so here we've got more than one of different types of atoms, different atoms from different elements. But because it's all bonded together, this means that this is one molecule. So although there's lots of atoms have gone into it, it's still only one molecule of this. And it brings us into a thing to note of these. Do you notice before that all of these symbols start with a capital letter? And that's very important because that would be the only way that we could tell the difference between, say, oh, we had one earlier. So let's take tin, a symbol of SN. Again, does not contain an S. But tin for SN. Now you see the first letter is capitalised and the second isn't, it's lowercase. Now if we didn't lowercase that second letter, or didn't capitalise any of them, no one would be able to tell the difference between tin and a compound made out of sulphur and nitrogen. So you see the great difference that this can have. Just by a simple error of not putting a capital letter on something, it would greatly change what someone thinks they're reading about. So that's the first thing to know of any formula we see, is that they always have a first letter at the start. And so what it means is that we know that Na is not capital N and capital A, meaning two different elements. Now the second thing to know is these numbers down here, called a subscript. Now I'll list these a little bit later, but these numbers down here are kind of like the ingredients list from a recipe. So we can see here that we've got two atoms of sodium in this. There's no number here, so that means there's just one for sulphur. And then under the oxygen we've got 4, meaning there's four atoms of oxygen in this compound. So if we change any of these numbers, it could change what we view this molecule as. It could change the compound completely. Now, an example of this, to take it away from the complex explanation, is imagine we described cars like this. So on some cars, you have 2 doors. Some cars, you have 4 doors. Most cars come with 4 wheels, so that's just for sake of comparison. Now if we change that number there, then it would change what type of car it was. It would no longer be a 2-door car. And likewise, we could have 2 of these, which would be 2 small cars next to each other. But if we just doubled these numbers and kept them in this format, so say we put a 4 here and an 8 here, well then that'd no longer be a small car, because a vehicle with 4 doors and 8 wheels is a truck, or something very different to a small car. And it's important to remember that this here, for it to remain as it is, it's got to stay as it is written. We can't change these numbers underneath here, because otherwise that would greatly change what it's representing. So to see that, who thinks here, with the previous lesson in mind, who thinks here that that is correct? because we have the same number of parts on both sides. With 4 hydrogens, H's, and 2 oxygens, and on this side we've got 4 hydrogens and 2 oxygens. So are they the same? Are we talking about the same thing here? Anthony?
I don't think so, because H2O is just water,
Yeah.
but I'm not so sure what H4O2 is.
Yeah. So like the previous example, this would be like having 2 small cars. Now if we just double the number of things inside of it, that doesn't give us another 2 small cars, it gives us a vehicle that's much, much larger. So this represents 2 molecules of water, but this here isn't chemically possible. This would never work in any kind of real world. You know, to make a sort of a clearer sort of case for that, here we've got 2 unicycles. Now say if we did the same thing, the important thing is number of seats and the number of wheels. So here we could say that we've got 2 unicycles. I mean, we've got 2 wheels and 2 seats. So would that mean that that's exactly the same as this? We've still got 2 wheels, we've still got 2 seats. But you see, the fact that they're now connected changes completely what this vehicle is. So let's learn how we can represent the difference between having 2 unicycles and a tandem bicycle like this. Is not by changing the small numbers, but actually changing this number here. So this number on the left is called the coefficient. Now this, as we saw before, shows that there's 2 molecules of water. If we can't simply just double the number of things in here, because again, it's the difference between that and that. Just by doubling the number of it doesn't give us, these are completely different vehicles. So, just for summary, what was this little number below called? Anthony, please.
Subscript.
The subscript. And can anyone remember what this larger number to the left of the molecule was called? H?
The coefficient.
Yes, the coefficient. Okay, so what we're going to do is next is an exercise. We're just going to quickly go through subscript and coefficient once more, just so that we've got this clear. Okay. So worrying about what it does to the thing isn't so important, because the subscript is the number of atoms in the element of the number of atoms of the element in the molecule. So how many of one particular element is in the molecule? Think of it like with any recipe, it would be like the weight of a single ingredient that goes into it. If we change that, well, it will affect the outcome of the product. If you double the amount of flour in a bread recipe, it's not going to come out the same as before. But say that we wanted to make 2 loaves of bread. Well, that's where the coefficient would come in. What was the coefficient used to show? Or where did it go on the molecule first? Where would you place it? So the subscript was the little number below, the coefficient was the number to the left. Yeah, I've answered that, haven't I?
It's the number. It's in front of the. It shows you how many molecules there are.
Yeah, so it goes to the left of it, and that shows how many molecules are. Okay, so we'll just go through this quick exercise. We won't worry, if we have time we'll go through this right hand one, but we'll start with the left. So on this first one here, how many in total that we've written here, how many H's are there? How many hydrogen atoms are there? Tracy? 2. And how many oxygen atoms are there in this molecule? H?
1.
1. Okay, so let's mix in with the coefficient. So in this one here, in this total amount, how many carbons, how many C's are there within this total amount, not just within that molecule? Anthony?
2.
2. And what about oxygens, or O's, in this? And what is the total number of them? Paige?
4.
4. Because what we've now got is, we've got 2 molecules, each containing 2 oxygen. So they're just times together, these numbers. And then what about this? How many carbons do we have in this total amount? Anthony?
3.
3. And how many oxygens do we have? Paige?
3.
Right. Now what if I asked you, how many carbons are there in just this molecule? I can see you all sort of doing a number 1, that's correct. There's only 1 carbon in that molecule, but we have 3 of them. So that's why knowing the definition of a molecule is important, because these things can catch you out on a test or in your understanding of the subject. And what about here then? We'll do these as well. How many hydrogens do we have in this total amount? Paige?
4.
4. How many oxygens do we have in the total amount? Tracy?
2.
Well, don't forget, we've got 2 of these molecules. And how many oxygens in each molecule? Anthony?
4. 2 times 2.
Yeah, 2 times 2. There's 2 oxygens in each molecule, and this number here means that we've got 2 molecules of it. Okay, so we'll move on then to our summary of this. So, how would you describe, I'll move over this side, how would you describe an atom? Anthony?
It is the building blocks of all elements.
Yeah. All the other elements are just made up of different types of atom. Oh, that didn't work. What about elements then? How would you describe an element? Or how would you describe the difference between an element and a compound? Paige?
Element is made up of one, the same, yes, one type of atom.
Yes. And so how does a compound differ from that? Well, do you remember what we said of what was the common usage of the word compound? It meant lots, didn't it, or many. So what would the definition of compound, when used in this, mean? Anthony, please.
This would be a mixture of different elements.
Yes. So it's more than one type of element that makes it a compound. And what about a molecule? What is a molecule? Anthony?
It is the smallest bit of a compound, or it's compound in its smallest form.
Yeah. It's a single unit of either an element or a compound. It's just the smallest amount of the bonded mixture. Okay, so when we dealt with formula, where did the coefficient go? Was it the one on the left, or was it the smaller one below the formula? Tracy?
The one on the left.
Yes, it was one on the left. What did the coefficient signify? Paige?
How many each had in the whole molecule?
Not in the whole molecule. It was how many there was in how many molecules. Oh, sorry.
How many of that element that they had? Is that right? Like, if you had the 2 before the hydrogen, it was 2 hydrogens.
No, that was for the subscript.
Ah.
So the little subscript below meant that, we'll go back to, so you see here this little number down below meant that in one molecule of this, the smallest amount, there was 2 hydrogen and 1 oxygen, because there was no number here. You see, when we had this number here, what did it mean? What did that signify? Anthony?
The number of molecules.
Yes. So this represents the number of atoms in each molecule. The one on the left signifies how many molecules of that. Just in the same way that you'd say there's 2 cars. With here, we've got 1 molecule of water, 2 molecules of carbon dioxide. Okay. Well, I'm afraid that brings us to the end of our session. There is a peer review form I'd like you to fill out, and next week we're going to a little bit more depth on this, using a couple more complex formulas that we might come across, and for the ones that don't quite follow the rules that we've followed in this. Okay, well, thank you very much for your time.
Good job.